It's calm, it's flat, and yet there are submerged canyons and underwater avalanches underneath, capable of forming mega-tsunamis. Have you ever wondered what would happen if you keep walking over there, towards the horizon, with lead soles to weigh you down? Okay, quickly you're going to lose your footing. But after that, imagine if you could breathe that you keep walking, always towards the open sea. Beyond 100 to 200 meters deep, you would reach just about anywhere in the world, a huge plateau called Continental, a vast expanse with almost non-existent reliefs and almost no slope. On these sorts of vast monotonous plains that border almost all of our planet's continents, to cross a stone, a semblance of relief, is already in itself a small event. Sand and sediments have accumulated here, transported by winds, rivers and tides. For millions of years, these regions, the submerged foundations of continents, are shaped by the energy of the swell, storms and tidal currents that every 12 hours, in a slow and continuous back and forth movement, sculpt them. But if you continue to make further progress through these vast flat expanses towards the sea, then you will end up on a strange slope. The start of a gentle slope leading to the abyssal plains, located more than 3 kilometers below. The extent of these underwater plateaus facing the shore depends on the region of the world where you are. They can vary from a few kilometers to several hundred. Thus, if you were to leave Cherbourg and walk at the bottom of the water in the northwest direction, you would have to cross nearly 700 kilometers of this monotonous plain before slowly descending towards the abyss, at the level of the Gollum Channel system. Except that in some places, in this apparent monotony, there are shortcuts to go directly to the bottom of the oceans. Under the waters of the Bay of Biscay, there is something as enormous as the Grand Canyon. In this direction, under the horizon, begins only 300 meters from the shore one of the most imposing underwater structures in the world, the Cap-Breton Abyss, a canyon located under the water, bordered in places by cliffs nearly a kilometer high that snakes for 270 kilometers before reaching the abyssal plain 3,500 meters deep. If the Cap-Breton Abyss was on the surface, it would be all we could see. It was formed under the water, and from the shore, we can't see it. Just like this gently sloping cliff that we can follow for nearly 1,000 kilometers from its mouth, and which is regularly cut by hundreds of other smaller underwater canyons that follow one another, and also dive from the continental shelf down to the level of the abyssal plain located in this region, 4,000 meters below. In fact, even though the measurements of the Cap-Breton Canyon are exceptional, it is far from being the only one of its kind. And all these gashes that we have just flown over, with their steep relief and nearly 100 kilometers long, are themselves just a small part of the some 8,500 underwater canyons identified on land, or rather under the seas. And here we go for a quick tour below the horizon of the most prominent ones, starting with one of those whose vertiginous reliefs are so vast that they can literally be seen from space. I named the Great Bahamas Canyon. Here, the dark blue channel that we distinguish at the top and center of this image reveals the presence of extremely deep underwater funds. Consider that the walls of this canyon that dive near the islands between which they meander are 5 kilometers high in places. On dry land, there is no equivalent vertical structure. And these giants of the oceans, we have, by means of autonomous rovers, begun to explore them in the past few decades. And what we were able to discover there is mind-boggling. Here, it does not rain, it does not snow, but it is not uncommon, when exploring them, to find oneself caught in underwater avalanches. The first few times the autonomous rovers encountered these phenomena, they saw their screen inexplicably blur, and initially believed it to be a hardware malfunction before realizing that their camera was working fine, but was caught in a large opaque cloud of suspended particles, caused by the flow of turbidity currents, the scientific term for underwater avalanches. Thus, sediments often slide down these corridors here, often accumulating near the entrance of these underwater canyons, which, just like those in the open air, serve as channels for flow and host currentless wells. Off the mouth of the Congo River lies a vast submarine canyon of the same name that crosses and deeply incises the entire continental shelf, ending its journey nearly 300 kilometers from the estuary. Here, within these gorges and during the river flood periods, the strongest and fastest turbidity currents in the world have been measured. With an average flow speed close to twice that reached at peak by a swimming champion, these underwater mud and sand avalanches can carry particles from both the river and the continental shelf with them, over hundreds of kilometers beyond the canyon's mouth. In fact, even though the smallest among them are only a few meters thick, the largest can reach several hundred meters in height. And these mud and sediment storms racing down the slopes can last for hours, or in exceptional cases, flow for several days, feeding themselves along their trajectory. Because these deluges from the depths are capable, often advancing with all the power of a steamroller, of amplifying themselves along their path. By tearing particles from the terrain they encounter on their way, they can, like a snowball effect, end up taking on truly gigantic proportions. The most imposing of them being capable of setting in motion millions of cubic meters of sediment. This can give rise, over time, to immense deposits which, avalanche after avalanche, have accumulated deeply, sometimes kilometers thick. Thus, the sedimentary fan spat out by the Grand Canyon of the Congo into the abyssal plain covers nearly 300,000 square kilometers, an area as vast as a country like Italy. In 2016, an earthquake that struck the south of New Zealand caused avalanches in the deeply incised Kikura Canyon, which then travelled more than 600 kilometres past the mouth while depositing no less than 850 million tonnes of rocks into the abyssal plain, leaving behind desolation and death. Yet the abyssal fauna and flora of the deep sea, which in this region were swept away by the passage of mud and stone flows, quickly regained their rights. Paradoxically, these canyons that can turn into dead zones are also oases of life. Generally speaking, it is estimated that these ecosystems are 10 to 100 times richer in living beings than the surrounding deep sea, because these immense geological structures promote the mixing and blending of surface and deep waters. They concentrate minerals and nutrients. Here, more than anywhere else, life flourishes. And it is precisely because these rocky bleedings bring the deep ocean near the coasts that nearly 35% of the marine mammals that wash ashore in metropolitan France do so on the sole part going from the Garonne to Spain. Even if the Cap-Breton canyon owes its existence to the play of tectonic plate movements, generally, these incisions can be seen as extensions carved by the brute force of powerful rivers of today and yesterday. Because these canyons sometimes began their life near the surface, or even entirely in the open air, during the last glacial period, when the level of the world's oceans was 130 meters lower than it is today. This is particularly the case with the Hudson Canyon, which today is at the mouth of the river of the same name and progresses gently down the continental shelf, before it really starts to dive towards the deep sea, carving a deep notch about a kilometre high and then disappearing at 3,500 metres below sea level. But 20,000 years ago, the Hudson was flowing into the ocean, roughly here on the edges of the continental shelf, about 160 kilometres from its current mouth. Strangely enough, the size of underwater canyons is not necessarily linked to that of the river or rivers near which they are found. Thus, if this canyon, located off the most powerful river in the world, seems so modest compared to the flow of the Amazon that gave it birth, it is because it, now 320 kilometers from the mouth, is hardly fed anymore with sediments from the flow of the Brazilian giant, spitting and spreading its alluvium in all directions on the vast continental shelf facing it. By depositing an average of 1 centimetre of sediment per decade across this region, the Amazon has largely erased traces of the past, filled with these discharges from old and vast networks of underwater valleys. If here the river has erased part of the relief, it happens that elsewhere it is also the reverse. The most striking example is perhaps that of the Monterey Canyon, which snakes between steep and high walls in places, 1.5 kilometers, and this for nearly 150 kilometers under the Pacific Ocean, before spreading out by 3,600 meters below sea level. In fact, here, as in the case of the Cap-Breton abyss, we are dealing with a giant with no apparent family. In one case, as in the other, the sediment supply supposed to have cut into the rock to the point of forming these canyons is provided by rivers with flows far too weak, even over millions of years, to have been able to carve such structures. To form something as big over time, to carve such stone cathedrals, you really need to have a significant outflow. Thus, it is believed that the Monterey Canyon was aligned about 8 million years ago with a river rivaling the power of the Amazon. As for Cap-Breton, which is today associated with the small Lador River, whose output is absolutely not sufficient for these sediments to erode rocks over hundreds of kilometers, it largely owes its existence to the movement of tectonic plates. Thus, many of these geological wonders, so numerous that we cannot list them all, are the legacies of a turbulent past. Here, in the Bering Strait, the Shemsung and its accomplices concentrate and channel a large part of the volume of cold water flowing south from the Arctic. It's often hard to gauge the size of these huge fissures without a scale for comparison. So let's put a country like Jamaica next to it. And it's amusing to think that some of these underwater canyons are directly responsible for the currents they induce. From the formation of small water mountains that move on the surface, breaking waves. Like those in the north of Osgore near Cap-Breton, or even Praia do Norte in Portugal, which derive their origin from the presence of the Nazaré Canyon. A deep underwater trench, nearly 4,500 meters deep and 230 kilometers long, that acts near the shore like a wave amplifier and helps form water walls over 20 meters high. Huge waves that in the end are nothing compared to those formed by landslides. Because when particles torn by rain and carried by rivers, streams, currents, or wind accumulate to create unstable slopes near the slopes leading to the abyss, it happens that these precarious piles violently let go and start to slide down the slopes en masse. And these underwater landslides can have terrible consequences. In 1929, an earthquake off the island of Newfoundland caused a massive underwater landslide near the break leading to the abyssal plains. Monster clouds made up of mud and rocks of all sizes then slid down the slopes, carrying hundreds of millions of cubic meters of rocks, the displacement of which was even measured. Because a few minutes after the earthquake, transatlantic telephone cables began to break one after the other in the direction of their progression. And from the gap between each cable cut, we were able to estimate the speed of the flow down the slope at about 100 kilometers per hour. This terrible event deposited debris over 600 kilometers along the continental slope, to the point of covering an area the size of a country such as Tunisia, with a layer nearly 1 meter thick of rocks and sediments. By suddenly moving such a volume of material, this landslide caused a tsunami, whose waves of about 15 meters went to strike the south of Newfoundland, where they devastated the coast, killed dozens of people, and left over 10,000 homeless. And this in one of the least populated regions of our planet. As impressive as it is, this event is, however, pitiful compared to giant tsunamis caused by 3 of the largest known underwater landslides, and which all occurred within a few decades, 8,200 years ago. These so-called Storegga Slides took place on the edge of the Norwegian continental shelf, where their scars have been found, a few hundred kilometers from the current coast. It is thought that here, 3,500 cubic kilometers of debris and rocks from the continental shelf suddenly detached, before spreading over more than 1,000 kilometers west of their point of rupture. In sliding towards the abyssal plain, the movement of this mass, on average 100 meters thick and wide as Belgium, caused the formation of a mega-tsunami throughout the North Atlantic. Thus, on a large part of the Norwegian coasts from Iceland to the Faroe Islands, traces of characteristic deposits were found caused by the passage of a 40-metre high wave. In Scotland, it was repeatedly a wave of a dozen metres that penetrated in places up to 80 kilometres into the land. Storegga Slide, that's 2,000 times the volume of rock that was torn from Mount St. Helens during its 1980 eruption. If 6,200 years before our era seems distant, remember that on the geological timescale, it was just yesterday. Next time you gaze at the serene and calm horizon, perhaps you'll think about these marine landscapes which evolve at a sluggish geological speed, about these avalanches, these phenomena able to transport the most material at the Earth's surface and which are located under the seas.